This talk is about the EPIC scan record, and it's also about things you have to do in a database to make that scan record work. So there's a link to where to the scan documentation, to the basically where you can grab the code. And what's in it is the scan record, the rectin library, which is the original version of EPIC's retargetable links, written originally by Marty Kramer. There is the save data storage client and the scan parm record that I'll describe later. And there's also some EPIC's databases all about scans and scan parms. And there's a bunch of MEDM displays. So, what is a scan? I suppose I should define that first. A simple scan consists of the following. Endpoints times, you're going to do the following operations. Set a condition, it's maybe send a motor to a position and wait for it to get there. Start a scaler or some other detector and wait for that to finish acquiring. And then grab the data from everything, including the motors, the motor readback values, and all of the detector values. And then write the data to disk. When the scan is, in most cases, the data aren't written to the disk until the scan is over. You can tell it to write point by point if you want to, but most people don't. So that was a simple scan. A more complicated scan, a two-dimensional scan, for example, works like this. The inner loop scan is exactly what we saw on the last slide. And the outer loop scan, it basically only does two things. It sends a motor to a position and then triggers the detector, but in this case the detector is another scan record, and it just waits for the scan record to finish. So one thing you'll notice is that the outer scan is not saving any data. It's not recording any data here, because it doesn't have to. All of the data from the inner scan are going to be recorded multiple times in the... You actually can, if you want to, store data from the outer loop, but it's typically people don't. So save data is the thing that knows that this is a multidimensional scan. It's going to be monitoring both of those scan records. And it's going to look at the detector triggers of each scan record, and if it notices that one of those is writing to another scan record, then it assumes that this is at least a two-dimensional scan, right? It assumes those scans are involved in the same multidimensional scan. And it will write a multidimensional data set. So if you don't want it to write a multidimensional data set, but instead if you actually do want to do a bunch of separate scans and have them stored separately, you can arrange that by just not writing directly to the scan record's scan field or .exsc field, but write to some other record and have it write to the, have it start the scan, and then you'll write separate scan files. So scan features, there's going to be a whole bunch of them. You can have 0 to 4 positioners, which typically are motors. You can have 0 to 4 detector triggers and 0 to 70 detector signals. If you have 0 of all of those things, nothing's going to happen, right? But you can have 0 of any combination of those things. You can just use this as an oscilloscope, for example, and just have detectors. Or you can just use it as a manipulator and just have positioners. It can acquire from scalar or array PVs or a combination of scalar and array PVs. Scalar PVs are acquired on every data point. Array PVs are acquired at the ends. And if you do have an array PV, it only acquires endpoints, elements out of that array, because all of the arrays in a single scan record have to have the same size, same number of elements. The number of data points is limited by IOC memory. Used to be 2,000, and that limitation was imposed by channel access. But if you set EPIC CA max array bytes to something larger than 16,000, you can take more data points than that. I think the most that's ever been taken on an actual beamline is something like 300,000 or something like that. There's a detector client weight, which I think is probably ignorable. That has been overtaken by events. And there's a data storage weight for that's taken up by saved data. Pause and resume and abort. And I'll talk a little bit more about abort later. But if you abort a scan in the middle, the data are still going to get written. And the other thing is that the scan data are double buffered. If you start a scan and save data is still writing the data from that scan to the disk, you can start another scan. But then you can't start another scan after that until save data releases the first set of, that's only double buffered. Save data writes XDR format files. I'm going to give you more information than you want about that. And I'll probably skip through kind of quickly, and we can just use this as a reference for what that data file looks like. There's software to read it. But the important thing is that the network byte ordering problem is handled by XDR, so you can read it on any computer. A positioner can have private scan parameters. The scan param record, there's an example of that coming up in a little bit. But associated with each motor or each monochromator or any movable thing can be a set of scan parameters, and so you can execute a pre-specified scan with one button. And I'll show a little bit about how that works. After the scan is over, you can there are several options that I'll go through, but they include moving to a peak in the data, so you can do an alignment scan pretty easily. So a scan param record plus an after scan action basically is one button automated alignment for a single positioner, just one-dimensional alignment. Scan record's a channel access client. It doesn't do database puts of any kind. It could live in any IOC and talk to any IOC. It uses the RecDyn library, as I said before, to manage connections with PVs, and it uses CA put callback extensively. And so I'm going to be talking at the end of this talk about how CA put callback works and how Epic's execution traces work. And it uses get callback before acquiring the data to make sure that the data that comes, it puts monitors on all the PVs that it's going to acquire data from, right? But it does a get callback before to ensure that the data that are in those monitors came from after the detector trigger finished. Save data is also a channel access client, and it monitors scan records mostly, but it also monitors a whole set of PVs that you can list at boot time, and includes those PVs and their values in the data set, in every data set. The scan can run on all the operating systems we have. And you don't have to run the scan record manually. It can also be written by any channel access client. And this is generally true of anything that's in an Epic's database, right? Any channel access client can drive this thing or read what's going on. So in particular, it can be written by other Epic's records. You can have Epic's records trigger scans, program scans and trigger scans, and wait for them to finish and all that. So if you're writing some software to orchestrate a measurement, and that includes scanning of any kind, you can either do your own scanning or you can just use this stuff. There's also 2 extra links that have been added fairly recently. Before the scan starts, you can do some operation, and after the scan is finished, you can do some other kind of a cleanup operation. You can write any, this is just like a detector trigger. You can just write any constant value. And you can wait or not wait for this to happen. If you're doing a fly scan and you're starting the detector, that you wouldn't want to wait. You would just have the detector detecting all the way through the whole scan. If the scan record is part of a multidimensional scan, the before and after scan links for each scan dimension run every time that scan is executed. And an outer scan record can write to the outer scan record can write to anything in this scan record, of course, because the scan record is not doing anything when the outer scan record is executing. So the outer scan record can change the start and the endpoints if you want to, and it can write to those links and write to the values, anything in the scan record. And these links can write to their own scan record, but only to specified fields. It can write to the start, end fields and all that, but it can't write to any link fields. Oh, so I guess one example of that is if you want to do a back and forth scan, you can have the after scan link swap start and end positions, and then the next time that scan gets triggered, it'll just go backwards. So there's the user interface. Those are 3 instances of the same thing. There's a lot of buttons, right? And people really don't like looking at all those buttons. So you can condense it down to really not very much. There's still a lot of buttons. But there are some kind of simplifying things. All of the stuff in highway sign colors, the white on green, all of those things just bring up other MDM displays. So they're probably ignorable if you're just worried about executing the scan record. All of the things in pink are link fields. Those are RecDyn link fields. And all of the things in blue write to the crate or read from the crate. All right, so positioner options. There's a scan mode for a positioner. I'm going to go into that in some detail. There are three choices: linear, fly, and table. You can select absolute or relative, and those in relative, it's relative to the position the positioner was in before the scan started, before this instance of the scan started, if it's a multidimensional scan. And there's a delay if you want to. You can, and that affects all positioners. You can delay after the position is finished. And there is an after-scan motion that I'll go into later that affects all of the positions, and it determines what happens after the scan is finished to the positioners. So the positioner, the scan modes, linear is the usual thing. You just say, I want to acquire data on a grid of positions equally spaced, and you specify that with start, center, and with step size and endpoints. You can do any three of those guys. And the scan record will reconcile the other parameters. Table mode allows you to write an array of positions to be visited by a scan. And you have to have at least endpoints values in your array, otherwise the scan record will complain about it. And you don't have to write that array twice. The scan record will never touch it. And the other scan mode is fly. And this is soft fly. I'll show this in a little bit more detail in the next talk. It comes right after this one. But you specify the positions at which the data are to be acquired by start and end, and all the thing is going to do is go from start to end. It's not going to stop in the middle. And the algorithm is like this. You go to the start position, wait for it to get there, and then you launch everything. You launch the positioner to the endpoint, and then you start taking data. You start triggering detectors, waiting for them to finish, and reading their data, and also reading the position of the motor. And then you do that operation, endpoints, trigger and read, endpoints times. And so the timing of those data points is determined by how long the detector takes to acquire. And the readbacks from the motor are generally not going to be precise, because motors typically update at around 10 hertz. Sometimes you can change that. But what you're going to get is the most recent update from the motor that its driver did in its own little loop. So the positions are imprecise, but it's good enough for alignment scans. It's okay to mix scan modes. I don't think anybody ever does this, but in principle you can have one motor in linear mode and another motor in fly mode, that works, or in table mode. And the other thing is, this becomes more flexible when you realize that a positioner can be anything you write to. It can be a database. So you write a number to a database, and in this case, if you write the number 32, what the database is actually going to do is rotate and translate that sample wheel so that that sample comes into position. So it's not a motor really you're writing to, yeah, but you're selecting a sample, and you can do that kind of stuff with a scan record. You can also write to a positioner through an interpolation table, and I'll describe those next week, next week in the talk about calcs. Absolute relative is probably pretty obvious. Positions sent exactly as given or relative to the pre-scanned position. The settling time affects all the positioners, and what it does is it waits until all the positioners have said that they're done, and then it waits for the delay time, and then it moves on to triggering detectors. If there aren't any positioners, then that delay time is not used at all. The after-scan motions, 3 of them are independent of the data and simple. They just start. Just stay where you are, or go to the start position of this scan, or go to the prior position where we were before the scan even started. The other ones depend on data, and what the scan record does is it looks at the data from the detector whose number is given by the REFD field. And if, for example, you select peak position and the scan record finds a peak in that data, it will send the motors to where they were when that peak was acquired. And valley position is the same, except the valley and edge and minus edge are the same, except it's the derivative of the data, not the data. And the center of mass, something Pete Jamian added, is better than peak. It's got better precision than peak. But the center of mass will be different for different positioners, because the positioners included there in the equations, you can see. But it will, in any case, send all of the positioners to their points as directed by that first positioner. So detector triggers are pretty simple. There's just a name and a value. And it's just like the position or settling time. After all of the triggers have reported completion, the scan record will wait for the detector settling time, and if there aren't any detector triggers, it won't wait at all. So detectors should be even simpler, but there's actually a couple of options that kind of complicate things. There's 0 to 70 of these guys, and they can acquire either scalar or array data. And if you select scalar, and it's actually an array PV, it's going to collect an array at the end of the scan. The 1D array choice is really for all detectors being array valued, and it changes the scan effectively into a fly scan. Acquisition mode, I think, is rarely used, but what you can do is do a scan over and over and just accumulate the data in the scan arrays rather than starting fresh every time. So if you don't know how long you have to acquire data in order for it to get enough statistical precision, you can just set the acquisition mode to accumulate, and you just take data until the data look like they're good enough. I mean, just repeat the scan until you have good enough statistics. So client weight. So client weight is not really used very much anymore, I don't think, and I'm not going to talk about it. But it's there for posterity for anybody who really does. It used to be that clients actually saved the data, and so it was important to coordinate with clients. But now that the coordination with the data storage client is hardwired, and you don't really have to worry about it. And the coordination with clients that participate in data acquisition is pretty much done in databases with the busy record, which I'll show you at the end of the talk. So there also is an array trigger in wait. And this is for the case where, for example, your data are in a multi-channel scalar and they're not in EPICS PVs yet, and you have to tell it to read in order to get that into EPICS PVs. So that's what it's just like a detector trigger. It's just a name and a value. And scan controls are pretty simple. You write a 1 to it to start the scan record, and writing 0 to it would stop it in principle, but you really should use abort because it might be a multidimensional scan, might be other things going on. And the abort button, you can stop the scan record, but you can't stop the motors that it told to move, right? And you can't stop save data from responding to what the scan record posted. So the way abort works is the first abort tries to be really polite. It waits for the motor to finish moving, and it waits for save data to release the previous scan's data arrays. And the second abort ignores the motor. It just says, all right, whatever, you're going to have to deal with that on your own. But it still waits for the data because you don't want to throw away data if you can help it. The third abort kills the scan with no regard for consequences. And you'll normally lose data if you have to do that. So there's MEDM displays. If you can't remember everything I said, you can bring this stuff up and read it. It's not really the best documentation, but it's a little bit terse. But it's better to read the HTML file. So one-click scans. This is the scan params thing I was talking about earlier. Motors don't have to be set up this way, but typically at APS they are. Associated with each motor is a set of scan parameters, and that includes a start position and an end position and a number of data points, whether it's relative or absolute, and what to do at the end, those after-scan actions that I described, either stay or go to a prior position or look for a peak in the data and go there. And so what these scan parameters really are intended is for automated alignment, where you'll set a motor range within which you expect to find a peak, and with just one button you can execute a scan that goes to that peak. It's really pretty handy for one-dimensional alignment. So data storage is a completely separate program. Save data, monitors scan records, and it has a handshake with the scan record. It can stop a scan record from executing if it hasn't released the data buffers that scan record needs. Save data writes multidimensional array or archive files. I'll describe those in mind-numbing detail. I think you're going to hate that, really. And it automatically numbers the files, and if you it's got 10,000, up to 10,000. If you go over that, it's got another 100. So the location of the data files is different for different systems. On VxWorks and on RTIMES, you have to specify the computer, the NFS file server to which you're writing, and then you have to give a file path that's understood by that guy. On Linux, you're going to write to your own disk, so you just, or to whatever the system administrators have set up for you, so it's just a file path. You can't write to these things while a scan is in progress. Really bad things would happen if you try to do that. And the comment PVs, they look like they're saved, but they're only saved if they're included in the savedata.rec file in the IOC boot directory. So this is what that init file looks like. It's got a list of all of the scan records, and it's got a list of all of the PVs whose values and descriptions should be saved in every scan data file. And that's normally the only thing that you modify. It'd be nice if those were modifiable at runtime, but I just have been too lazy to add that feature. So this is the MDA file format. There's a header, format version, the number of this scan, whether this is a 1 or a 2 or a 3-dimensional scan, and the numbers of points of each of those scan records if it is a multidimensional scan. And then if this is a scan that has a multidimensional scan in which all of the detectors, all of the data arrays are of the same size. For example, it's a rectangular scan and each line is the same length. Then that's a regular scan. But if you arrange some software so that you scan a circular area, for example, within that, then there'll just be a few data points near the top of it, lots of data points in the middle, and a few data points in the bottom, and that's not a regular scan. And this is just an alert to clients that they have to be on the lookout for that, or to readers of the data file that have to be looking for that. So then at the bottom are all the extra PVs, is the name and the description, epoch type, and whether or not it's array, and the units and the values. The scan records, or the scan elements of this file go like this. At first there's a head, a scan head, which has got a whole bunch of information, number of points, the number of points you actually did acquire if you didn't acquire all the points you said you were going to acquire. Array of pointers to other scan records, if this is a multidimensional scan, the name, the timestamp, and then the number of positioners, detectors, and triggers. And then there's, for each one of those positioners, there'll be some positioner information that'll show you, and then later detector, and then trigger, and then finally the data. So everything that happened with this particular invocation of the scan record is going to be in that one area. It's not going to be strewn throughout the file. So more about that scan. Now the positioner is about what you'd expect, right? The names, the descriptions, scan mode units. The detector has the similar information. Triggers have only the number and the name and the command that was actually sent to the detector trigger. And then the last thing is the data, and it's just a bunch of arrays. For positioners, those are doubles. For detectors, no, they're all doubles. So there are data acquisition clients that can use the scan record. ScanC, which is maintained these days by John Hammonds, if he has enough time. It's not I think it's not a really firm commitment by anybody to maintain this thing. MDA Explorer is useful for data files that have already been acquired. That's Python software in the Synapse Utils directory. Don Arms wrote a couple of programs that can display data while a scan is in progress or after, or just from a data file. And David Vine wrote software that reads the data file and puts it onto a web page. Other data acquisition related software includes Area Detector, which is, as far as the scan record is concerned, it's just a detector. It's just another detector. And there is software to read and to manipulate MDA files. There's C code for that and also Python code. And both of those are in the utils directory. So completion reporting, this is the sort of second phase of this talk. So completion reporting is pretty important. EPIX has the ability to trace the execution of a database within an IOC. You can't trace execution that goes from one IOC to another IOC. It only works within an IOC, and I'll show you the consequences of that. The point of this part of the presentation is to show you how to write databases that behave correctly when somebody writes to them with a put callback. All right, that's really important for not only the scan record, but for any client that wants to start an operation and then go on to some other operation only after that first operation has finished. That's what completion reporting is all about. If you're writing a database, it's really easy. All you have to do is use process passive links for everything to trigger all of the execution in the database. And if you do that, you're automatically compliant with put callback. You're automatically going to do the right thing. Database operations that span more than one IOC, there's a couple of ways to do it. The easiest way is to use a record that knows how to write, knows how to do a put callback, that has put callback links. The scan record, for example, is one such, and I'll show you some other records too. But if it's not just a database that's involves channel access links, but there actually is some external channel access client that's involved in the operation, and I'll show you an example of this with CA Put Recorder next week. You can handle that as well, but you have to have a busy record, and I'll show you how that works in a minute. In cases in which part of the operation is driven by a CP link within one database, that's not different from the other case. The CP link is just a channel access client. So this scan record is going to do a put callback link, and that's the blue, green, double line, and all the other records are going to do process passive links, the black lines. And this database is one of those easy ones that's automatically going to do the right thing because everything is a process passive link. But it's still kind of interesting to see the order in which things happen. First thing, scan record starts that guy executing. It does a PP link. It starts the next guy executing. So this is not really fair, right? I mean, the last record is done, and the first record isn't finished yet. I mean, it started earlier, but it doesn't get to finish until everybody is done. So what happens is each record effectively calls the other record, and the other record returns. So that returns into the process routine of that record. So all these records will declare themselves to be done, and then it will tell this control will return back to the first record, and it'll do another set of PP links. Then that record will complete, and then the other link, that record will complete. And then finally, this guy will return to the original record, and it will complete, and Epix will notice this, and it will send a callback to the scan record. So that's how the database, the flow of execution actually works in this simple database. So if you have an asynchronous record, and what I mean by that is that it's going to write to some slow device support. And so it's going to process, send off a message to some serial device, and then wait to be called back from its own device support. But it's going to still be processing. It's just not going to be taking up the CPU. And that also works. You don't have to worry about whether you have asynchronous records in your processing, but it does change the flow of execution. Because this guy's only going to launch a command to, this guy's going to wait until device support calls it back before it triggers the next record. Right, so there's nothing left to happen here. It actually has returned, but those other records aren't done yet. So these guys do the same thing they did the last time. They start, finish processing, declare completion. And then milliseconds later, that device support returns and re-executes the asynchronous record, and it goes on with its operation and does a PP link. Then that guy completes, and this guy completes, and that guy completes, and finally Epix sends a put callback. So you don't have to worry about whether there's asynchronous records in a database. If you have an uninterrupted sequence of PP links, you're good. But if you have a CA link in there, and I'll show you this dotted blue line is going to be a CA link, and that's going to mess everything up. So just the same as before, but now we got a CA link. And this record that just did the CA link, it's done. It basically logged a request for a command to be sent to some record, and it's done now. But the processing that you wanted to trace is not done, right? I mean, the scan record actually wanted all of that stuff to happen, and it didn't want to have a callback until it was all done. So this is not going to be a good thing. And let me just go. This is always these three records here are always going to do the same thing. So this guy's not actually done, and this is a really easy thing to fix. So you can see this processing happens after the callback went to the scan record. So to do this right, you just need to use a put callback link instead of a CA put. Right? So a put callback link to the first record, PP link, and now a put callback link from that record to the next one. And that means these records can be in different IOCs if you like. And this could be, for example, a string sequence record or a string calc, something like that. Records that know how to do a put callback. And then nothing's going to happen because you have to have a channel access put, and that stuff is not going to happen until this database is given up the CPU. So we're going to have start, finish, and then finally channel access is going to get a chance to execute, and it's going to send a message to that record, and that record will start processing, and it'll do a PP link to the next record, let's say. And then when that guy finishes, Epix will notice, and it will send a callback to the client that started that, and then that guy will know it's done, and then this record will know it's done, and then Epix will send a callback to the scan record, and then everything's good. All right, so a put callback link is the thing that bridges IOCs. If you have an execution, a database that bridges more than one IOC, all you have to do is at the shore, you have to have a record that can do a put callback link. Yeah, it still is CA. For the string sequence record, for example, you have to have a CA link, as you said, and then there's a wait field associated with each one of those links, and you set it to wait or no wait, right? And the same thing with the string calc and the array calc. The SWAIT record automatically does a put callback, so you don't get to choose. And you also can do that with soft asynchronous device support, with any record. But it's less obvious to the user what's going on in that case, so I normally do it with one of these records. So what if some of the processing is happening with the channel access client? This is going to happen a lot with CA put recorder. Here's how it breaks if you don't do anything. This record is not actually going to trigger the processing. What's going to happen is this channel access client is going to monitor that little square inside this record, and it just puts a monitor on it. Whenever that monitor is posted, the channel access client is going to do something. What we want is for all of this processing to be traced, and that's not what's going to happen in this case. This record hosts its value, and it doesn't know that the channel access client is actually listening to it. Well, actually, it could find out, but it doesn't. And it thinks it's done. And then all the rest of the stuff goes as it's always done in the last examples. This record finishes, this record thinks it's done, and then Epix sends a callback to it, and then milliseconds later, the channel access client gets a monitor, and it starts executing, and it does a CA put, or it could be a put callback, it doesn't really matter, and causes all of this other processing that might be in a different crate, it doesn't matter. So these guys will finish, and this channel access client in this case is monitoring a PV to find out when the execution is done. And now everything actually is done, and it's just too bad because milliseconds earlier the scan record continued with what it was doing, and now you're screwed because it has moved on and it didn't wait for this process to finish. And this is also really easy to fix. All you have to do is add one record. And the rest of these guys don't even have to know about this record. It's the busy record is going to fix all this stuff. So this does put a PP link to this first record that's going to actually trigger the channel access client, and that guy does a PP link to the busy record and writes a 1 to it and says that it's busy, and now this busy record is just going to pretend to be doing something until somebody tells it to stop pretending, right? So it's not going to say it's done. All the rest of this stuff happens as before. But now the channel access client realizes that the monitor came. This is again milliseconds later. It does the same kind of stuff it did before, but now it's going to work. This guy finishes, that guy finishes, the channel access client gets a monitor and it knows that things are done. And now the channel access client, well, it's not, it has to write a 0 to this field. It does have to be modified in order to make this work. So the channel access client writes a 0 to the busy field, and that tells the busy record to stop pretending to be busy. And so it does. It completes. That guy completes, and Epix sends a put callback. So but I don't think there's really any cases of processing chains that are so convoluted that it's not possible to have the good behavior with a put callback link. So that's it for completion reporting.